Hi everyone. Welcome back to our physics class. Yesterday I explained for you how we can find the electric field for conductors. And I said I'm going to complete the class today to find the potential, which is the voltage for the conductors, and to discuss why this and what happened to the electric field and what's going to happen to that electric potential also. Today is 17 and 30. Then we're going to discuss electric field, electric potential, which is the same as voltage, which is the second part. In the third part, I will solve problems to make the concept more clear for you guys. Let us start. Let us start. Okay, I'm gonna just quick review for what I did yesterday. Just quick. Yesterday we talked about electric field, right, for conductors, and we explained that the charge for the conductors stays on the surface of the conductor. Because of that, we have no electric field inside the conductors. I explained all this for you yesterday. Then all this explained yesterday, and we found that the electric field graph here between the electric field and the distance from the center is 0, then drop in this way. Today our class will be about voltage and electric potential. I have too many spheres to explain the concept. Let us start. We said voltage. Okay. Before I start the voltage, I need to give you the relation between the electric field and the voltage. Electric field, which is E, is a vector quantity. Which is we don't have to apply the type of the charge, the type of the charge in the formula. And like negative or positive, just we keep it always positive. And we have to find the direction. And this is what I discussed in different videos. Go back to the electric field for point charges, you will see how we deal with the direction. The voltage here, the voltage is V. The voltage is V equal, look here, in simple way, V is a scalar quantity. Voltage scalar quantity comes from the dot product between two scalar quantities, E and R, which is E R cosine theta. Now if there is change in the voltage, that causes the change because the R changes. Look here, if R changes, the distance change, the voltage changes. I can write V, delta V, I'm gonna write like this. I need this very important for me, for you and me. Delta V, which is change in V, delta mean change, equal E delta R. Good? Now R is a vector quantity and E is a vector quantity. Then E is delta V over delta R. Okay. Remember that R is a vector and V is a vector. Now, depend on this, I'm gonna explain my class. Now, here, that's my circle and this conductor. Then as we explained that the charge will be here. Yesterday, or last video, we said E inside equals 0. Right? Today we're going to find the voltage. V, the voltage from the center of the circle, which is O, till the radius R, which is R, the surface, V from 0 to R is constant, the same value. We need it to be constant. Why? Look here. We said 0, go to the formula, E, back to the last one. You will not find this anywhere, this explanation, delta V over, well, delta, here is R. Delta R, in this case, is the radius of what? This guy here, delta R in my case here, is the radius. And we know this 0. Equal delta V over R. Cross multiply, delta V equal 0. Delta V means V2 minus V1. That means the change in electric potential between any 2 points. To have this change equal to 0, that means V1 equal V2. Wow. Then if you take any 2 points, anywhere you want, if you take any 2 points, anywhere you want, let me extend this line a little bit to make it organized for you. Okay. I'm gonna add 2 minutes for this for you guys. Okay. That means, look here guys. That means if you take the 1 and 2 at anywhere here, or this point 1 and this point 2, between 1 and 2, the voltage is the same. You see that? Why? To get E equal what? To get E equal 0, which is the one we did yesterday. But the value of the voltage then? What my value of the voltage? What my voltage value? The voltage value, which is the same. If I put 1 here, or 2, or 3, or 4, or up to the surface, V equal K Q over R, which is the radius of that. Then the voltage you will get at any point from the surface up to here, from here to here, is KQ over R. Remember, if Q negative, apply negative. If Q positive, apply what? Positive. Good? Okay. What's gonna happen after that? If we want the voltage here, somewhere here, away from a distance equal a distance, then we know this R, and this is the center, and now we need a distance D from the surface of the sphere. Okay, then look here, we're gonna say R. I'm gonna keep the same color. We're gonna say R plus R plus D equal a big D. Then V equal K Q over D. Remember, D equal R plus D. Now as D increases, D increases, D increases, V decreases. Then let us call this point A and this point B. Then V at A is greater than V at B. Let us choose another point, more distance. R, I'm going to take a little bit distance. Then this is D, and D now at point C, equal R plus the other D. Now D is bigger than this D. You see the distance from here to here, you see the distance and the distance. Then V, the same formula, K, Q over D. Then VC less than VB and VB less than VA. But VA is this on the surface. On the surface, from here to here we have the same value. Now let us see how we can graph this. I have the graph here. Let me just get the graph out. I need to make it close to here to discuss it with you. Okay. A little bit more. Okay. Okay. Now this is y-axis stand for the voltage, and the voltage, the unit for the voltage is volt or Newton for the electric, Newton per column, right? Newton meter per columns. Newton, let me just fix it here in different color. Newton meter per column. From the zero, we have V here on the surface, V at R, I'm going to call it. This is the same value, the same value, the same value, the same value. Then from here to here, we have a constant value for the voltage, which is this value. Make it thicker, make it this color. Then after that, it's going to be decreases, but decreases on this rational function 1 over D for this, for the voltage. For the electric field was 1 over D squared. This guy goes faster, goes what? Look here quickly. This guy take his This takes the time, it's time. Look here. This takes his time a little bit. The other curve for the, if you remember, the other curve for the d squared was, I'm gonna do it and I'm gonna erase it. I'm gonna do it. This is for the voltage. For the other guy, go a little bit faster. Okay? I'm gonna erase it. But you see that this is for the electric field and this for, and for the electric field, there is no such any electric field in here. And I explained this before. Okay. Now, that's the last thing I'm going to say. To know why the electric field in the sphere is equal to 0, I'm going to just quickly do something for you. Electric field is 0, the last thing before I leave you alone. Okay, I'm going to draw. If you remember my class, the first class in electric field for this conductor. For insulator, we use Gauss law, right? But for conductors, the charge will be here. To find the electric field, you have to use the Gauss law. Why the electric field inside 0? Because if you want to choose, if I want to find the electric field at this point here, I have to have a Gauss surface, Gaussian surface, right? Okay, how we can find the Gauss surface? I'm going to take a copy from this. Then minimize it a little bit. The Gauss surface had, oh, good job. Okay, this is my Gauss surface. Gauss surface has to be the, you see the Gauss surface here? This is my Gauss surface. And I have to look if I have any charge in the, do you have any charge inside this guy? No charge, because the charge, because that E equal 0. Have a good day, guys. Have a good day. I will give you more about this problem, solving a problem for this field, conductors, and have a nice day.